chapter 7 test. So we have tin in a tin salt aqueous and zinc in a zinc salt aqueous. And so we go up into the table and we find a reaction between tin 2 and solid tin and zinc 2 and solid zinc. And one of them has to turn around from the reduction value and be the oxidation value, because something has to be giving these electrons. And I know I need a positive value when I get done with that. So I'm going to turn around the one that's going to be more of a positive, and that's the zinc. That means that's the anode. And the only way I can remember this is that anode and oxidation both start with vowels, and reduction or receiving and cathode all start with consonants. And so now that I flip these and change the sign, I get a positive delta E standard value in volts. In number 2, aluminum is going from a solid, which is charge 0. If you didn't remember that, then write that down, to +3. That means it lost electrons. So I'm looking for the flipped version of this to that. Up in the table, it will be this to that, but I have to turn it around, which means I get a positive value from that. And then this one is getting reduced. It is receiving the electron. So I keep the value and I add up the values for E standard. This is equal to E standard. This is equal to E standard, or E naught. In 3, the X metal is decreasing in mass. That means it's getting oxidized. Electrons are leaving it. It's going into solution. Atoms are turning into cations and leaving the stick of metal X. Therefore, I'm going to know that that's the oxidation half reaction in this total. So I know that the lead is the reduction. So I'm going to look up in my table, find the lead to lead +2, keep the value. I know that the total is this, so this equals the lead reduction value plus whatever it was from the X. Now I put Y here because I didn't want to make it seem like I'm putting in element X, so I chose a different variable. But the value from the oxidation of element or metal X. Here's the big trick. When I do that, I find the value for the oxidation version of using metal X, and they asked for the reduction. Where is it? The reduction value. So it's the opposite sign of the value I found. On number 4, we have no solid nickel. We only have aqueous +2 nickel. So the only thing the nickel can do is go from cation to solid to charge 0. The nickel must be the reduction reaction. These two can only go from solid to cation. They must be the oxidation reaction. And if anything's going to happen just naturally, when we look at the E standard values and combine them together, we must be getting a positive value. We must have a E standard value that gives a thermodynamically favorable reaction, and that is a positive voltage when we get done adding it up. Let's look at the nickel, and remember, we're going to keep this because it has to go to solid. We have no solid originally, and that's a negative 0.25. When we look at the lead, we're going to turn this around, I know, but it's only a 0.13, and when I get a positive that and negative that, I don't get a positive value overall. But when I use the zinc and I turn this around, that becomes a positive 0.76. And when I add it into the nickel value here, I do get a positive value. And this is a reaction that nature would do. And so zinc will be affected, but the lead will not. Here, we're going to find delta G standard, and you need to go look through your table of equations probably, but there is one of delta G standard equals NFE. F is just Faraday's constant. You just go look that up. It converts between coulombs of electrons and moles of electrons, because when we discuss balanced reactions, we don't have coulombs. Yet, when we say E standard here, that should be, it's in volts, and a volt is a joule per coulomb, and they absolutely think you know that. Your canceling will not work. Some realizations probably will not happen if you don't know that a volt is a joule per coulomb. A coulomb is just another group of electrons like a mole is, except obviously it's a lot smaller, because look how many coulombs it takes to be equal to 1 mole. So that in the way that a couple is less than a dozen, and yet you can measure the same things, a coulomb is much smaller than a mole. but it measures the same thing. And that's just because the physics people, when they decided to invent the concept of voltage and so forth, ended up counting how many electrons it turned out they were using. The story is much more complicated than this, obviously. And it turned out they were using what became known as a Coulomb. So a volt, which measures E standard, is a joule per Coulomb. It's the pull or push, whichever way you want to view it, of electrons such that every Coulomb of electrons affected this way will provide 1 joule. Also, an amp is 1 Coulomb of electrons going by per second. Write that down also. So, what do we know about this? Well, this is getting reduced. This is getting oxidized. This is gaining 2 electrons. This is losing 1 each, but it's doing it twice. There are 2 electrons being exchanged. For every mole of times this happens, 2 moles of electrons are exchanged. So this is a 2. So there are 2 moles of electrons per mole of reaction. And that's an interesting little but kind of significant point, in that delta G is rated in joules or kilojoules, but same thing, per mole of reaction. And what I've just proven is that for every 1 reaction that runs, there will be 2 electrons exchanged, or for every 1 mole of reactions that happens, there will be 2 moles of electrons exchanged. Then this cancels out the moles of electrons, and this cancels out the coulombs, and I end up with joules per mole of reaction, which is the proper units. There we go. And we know it's mole of reaction. You can put reaction if you like. I don't think they'll care on the test for delta G. Also, this was also, note to self, this was a negative, which I forgot originally. And so what we end up with is negative 2, which cancels out this negative here that we found by adding up the E standard in the table. And we get a positive kilojoules per mole of reaction. This reaction is very much not favored. Of course, you would have known that by the E standard value, huh? All right, 6 is a biggie, and it kind of has 2 stages. I want to do it one way, like it's a multiple choice, and we just know the general idea of the information, and then the other way where it's a free response, and you got to do everything the hard way. So we know we have these chemicals and these ions. Go find your reduction potential values, and we know that we need to add them up such that they get a positive value for volts. We're going to have to flip one of them. It turns out you need to flip the silver so that this becomes a positive. And then when we add them up, we get a positive voltage for an E standard. Now that's important because then I know which one is getting oxidized and which one is getting reduced, and I know which ion is the product and which is the reactant. So this ion is the product and this ion is the reactant, so that when I know which one to put on top. And that's important because in the balanced overall reaction, which you probably kind of have to sketch out or you're going to get this wrong, this is going to have a squared value in the Q math. Why do I know that I need Q math? Where did Q come from? Well, what really affects the cell potential, the cell voltage, is the ratio of the cations, and that is Q. Take a big note, but what changes the standard cell potential to the current cell potential is the Q value, the ratio of the ions. And once again, standard cell potential is measured where the ions are all at 1 molarity, so then Q by definition is 1, which is also what we said in the middle or so of this chapter, talking about delta G standard. Q is 1 at standard conditions. In this case, why? Because the molarities are all 1. Well, this is not a standard conditions, and the voltage is probably going to change. I know now that the product ion is the copper, and that will be to the power of 1, and the reactant cation is the silver, and that will be to the power of 2. If you get this backward, you're going to get the wrong Q. One of these cancels out one of those, which is 1/2 now, which is 2. Q is 2. Now, if we just stop right there, that's more like a multiple choice question. And they might ask something like, what is a possible current cell potential? And they'll give you something like the E standard potential, hoping that you'll say, oh, 50 and 50. It cancels out to 1, and therefore Q is 1. This must be standard conditions, but Q is not 1 because you forgot to square one of them. We know Q is 2, which is bigger than 1. This is not standard conditions. And if it's bigger, if Q has gotten bigger, that means there's more product. Or less reactant, or both, right? Now, what also makes sense is that as a galvanic cell does its reaction and proceeds on and on and on, of course, it makes more products and it loses reactants. And it's coming toward the state of being dead. The cell potential is approaching 0 at all times while you run it. We know that Q is getting bigger as you run it, and we also know that the standard cell potential currently, the current conditions, is approaching 0. It's going toward equilibrium, so Q is approaching K, and when it hits K, the E potential of the current conditions of the cell will be 0. Or to boil this right down into a note you can take, if Q for a galvanic cell is bigger than 1, you have lost some cell potential. If Q is smaller than 1, you have gained some cell potential. And by that, I mean volts, voltage. So this is going to have a current voltage potential that is less than the standard conditions. Now, probably not by a lot because, as I said, Q has got to approach K. This will all come to a stop when the cell hits equilibrium, and that's when K is true. But K for some of these cells is in the thousands. So the change from 1 to 2 is probably not going to affect it much, but by definition, the current cell potential measured in volts must be less than what we get here. So then they would have choices that are equal to the standard cell potential, and then 2 that are greater, and then 1 that is less. And you just say, oh, if Q is greater than 1, then the voltage has dropped from the standard conditions, and you choose the one that is less than the standard value. Now let's move on and let's actually calculate the sucker. And now I know Q. I also know E standard, and I can find this formula. That's a given. If this is 25 Celsius, then that's given to me. I discovered that this is 2 electrons per reaction, or it's 2 moles of electrons per 1 mole of reaction. Faraday's constant is a given, and Q is 2. I've punched this through twice. I think I'm right, and we end up with a current value that is slightly less than the voltage we had for standard conditions, like I said. On 7 for the cathode, where reduction takes place, we have basically 2 choices. We can either reduce water or sodium. You can't reduce the chlorine ion in the water because that would result in a Cl-2, which is not going to happen. So this is not an option. That is off the table. You can either reduce the water, and there's your reduction value, or you can reduce the sodium, and there's your reduction value. So if you're pumping electrons into salt water, what's going to happen first, by a long way, is you're going to reduce the water and produce hydrogen gas at the cathode. For how long it will take, you need to end up in seconds. Well, what kind of information in here has seconds built into it? Well, amps does, and they very much think you know that an amp is a coulomb per second. So they have handed you seconds. This is 8 coulombs per second. So inside there is your seconds unit. So you know that that's going to have to turn over so that seconds come out. And after that, it's kind of a cancellation process and exercise. So I need to cancel out coulombs. And the thing that's going to work is Faraday's constant, not just because it has coulombs in it, but because it's the bridge between moles of electrons, which I'm going to get out of here, and coulombs, which is going to cancel that out. Now, why would you have moles of electrons? Because we know how many copper atoms charge 0, we're going to form. We're going to plate 1/10 of a gram of copper solid, charge 0. That means we're going to use 1/10 of a gram of that. It doesn't really matter which one you use. We have 1/10 of a gram of it. The molar mass is essentially the same. Electrons don't count for enough to matter. This converts me to moles of copper, either one. The electrons we'll use is double that. So just for pretend numbers, if we had half a mole of this, we could run this reaction half a mole of times, and we'd use 1 mole of electrons. Well, it turns out we'll use whatever that is, moles of copper ion, and we'll use double that moles of electrons. So this gives me moles of electrons, and Faraday's constant is the bridge between moles of electrons and coulombs. And when this all cancels out, I get seconds it takes to perform all this. This is something similar, except I want grams. So for grams, I'm going to need to use the molar mass. What do I know? I know amps. Amps is coulombs per second. And look, they give me time. So I'll take my time, convert it to seconds. My amps here as coulombs per second cancels out the seconds, gives me coulombs, and this as Faraday's constant is my bridge between coulombs and moles. Now I have moles of electrons, and there is 1 electron for every 1 ion or atom. That gets me moles of ions, and I can convert that to grams. Read through this. The electrode that is increasing in mass is supplying electrons to the cations in solution, which are moving toward it, picking up electrons and sticking to the electrode as solid. So that's a reduction, the picking up of electrons by the cations. That's the cathode. And that means that the electrons are going this way, by the way. They're arriving there. That's why it has so many electrons to give, which means they're coming out of this one. This one will be gaining mass. This one will be losing mass. Why? Because it's losing electrons, and therefore solid, charge 0, tin atoms are letting go and becoming cations in the solution. And boy, do they think you know all of that for these kind of problems. Any of that is on the table to be asked. So oxidation is occurring at the tin, and that means that it will be losing electrons. And the decreased mass is in the solution, which is what I said. For C, you might go look at the galvanic cell diagram. The left beaker is losing cations in solution, so the cations in the salt bridge are going to be drawn that way. The right beaker is gaining cations, which means it's getting overloaded with plus charge, which will attract negative ions to the right beaker. For I here, you're going to have to at least mentally write out the full overall equation. I would write it out for real, just to be safe, to prove that you know that the coefficients are all 1. So when you take the molarities, the given, and put products over reactants, you know you don't have to square anything or something. So we end up with 0.5 over 0.5, which is 1. And again, the current cell potential is really governed by the value of Q. If Q goes up, the current cell potential went down. They go in opposite directions because if the products are building up, then the cell is being used up. If the product value is going up, Q is going up, but that's actually less of the cell's chemicals left to do any work. It also makes more of a pushback for the electrons as the products build up in molarity and the reactants fall in molarity. Now, double I poses a tricky question. I am not contradicting myself from before. The current voltage is still the same as the standard cell potential because Q is 1. However, and you might need to pause and have a deep think about this and ask me other questions, but that cell will run for a shorter time. And here's my illustration. If you're using up 0.01 molarity per minute, okay, well, using it up in 0.5 and 0.5 creates a bigger percentage change than if this number was 1 molarity and 1 molarity. And for instance, if this number was 4 molarity and 4 molarity, then your current rate of use would be an even smaller percentage change on the molarities. So running the cell will have a smaller effect if the molarities are greater. So the voltage will change to a smaller extent per minute per second because Q will be harder to change if you use greater molarities. And obviously, if you use a bigger battery with big molarities, it's even harder because the more chemicals you have, the harder it is to change half of it, isn't it? So car batteries don't just use some little 12-volt battery you can hold in your hand. They use something with a lot of chemicals in that. It's got a lot of sulfuric acid and lead. That's why it's so heavy. It uses lead. Lead is pretty effective and it's cheap. And if it's going to only go in a car, no one really wants to argue about the weight. But my point is there's a lot of chemicals. And if you start off with a lot of molarity, then it's hard to change the Q value, which means it's hard to run the battery down to equilibrium where the current cell potential is 0. I had to have a bit of a think about what they mean here. And it's tempting to say, oh, it's 1 molarity. I need to find Q and so forth. What they really are saying is that they're just putting this stick of SN solid into this solution with this cation. So it's not really a galvanic cell in that there's no wire and there's no second beaker and the electrons will not be passed through a voltmeter or any of that. We do, however, have the possibility of a redox reaction or an electron exchange. So what would it be? Well, this is the only solid and that's the only cation available. So we're going to go in here and find those. Here's the copper cation becoming a solid. Get the right one, by the way. That's a copper +2. And here's the only one available with tin solid. We're going to have to flip this. So this is going to become positive 0.14. And then we have a positive, and they add up to a standard cell potential of 0.48 volts. So it is thermodynamically favorable. And don't forget to follow the instructions and write out the net ionic equation. That's the net ionic equation. The electrons do not appear. They cancel out. Make sure that they cancel out, but it's 2 electrons and 2 electrons, so they do cancel out. Otherwise, we might have to multiply one of these, which would not multiply the voltages. Remember, that would not. But that for the net ionic equation, you might have to multiply one of these lines, which would then appear multiplied in here. For double I, there's not a lot to it once you realize we've just discovered the value for E standard potential. And then we find this formula, then we know N is 2 electrons. F, of course, is given to us as Faraday's constant. We just discovered this number. Just double check that everything's canceling out and you get a value for delta G. Do not forget the units. Make sure that you're getting joules per mole or kilojoules. You could call that negative 92.6 kilojoules per mole.